So we are on page 6 here. And now we formally get into what is officially a limit. And we've talked about it informally already. A limit is just a value that you can get arbitrarily close to. Like when I walked half the distance to the wall, I was getting arbitrarily close to the wall. And we said if you did this forever, you eventually would be so close to the wall that we would basically say you are at the wall. How do we write limits? Well, we have this notation where we shorten the word limit. You'll notice mathematicians like to shorten words so they don't have to write as much, to LIM. And we say the limit as x gets close to a of whatever equation we have is equal to some number. So the f of x right here could be any function, any equation, any expression. And what it's equal to is what our job is, to try to find out what number it gets close to. So we're on page 6. And you just have to fill in what's in that box. So some limits are extremely easy to figure out. You can figure out a limit if you can plug in the number and evaluate it. Like 3x minus 8. Well, what happens when x gets close to 5? Well, we know that when x is 5, 3 times 5, 15, minus 8 is 7. So we know that if x is getting close to 5, our answer would be getting close to 7. If we look at this graphically, (3x minus 8) is a straight line. And on that straight line, if we plugged in the point x is 5, we would get the point 5, 7. The idea of the limit says, man, if you are getting close to it from this direction and close to it from this direction, when you're getting close to 5, what is the y value getting close to? And it's really obvious to see from the line, it's getting close to 7. So as a general rule is if the function is continuous at the point x equals 5, in other words, it's not, the graph is not broken up into a whole bunch of different pieces. We'll get into graphs like that in a bit. But if the graph is just nice straight line and you can plug in the value, then that's your limit. And those limits are extremely easy. We're not going to do hardly any of them because they can be figured out right away. So a continuous function, as I said, this is the not real mathematical heavy definition. A continuous function is a graph or a function that you can draw without lifting your pencil. Okay? You can hear from the definition why that's not a very technical mathematical definition. But if you were drawing something like a 1 over x graph, a 1 over x graph looks like this with asymptotes. But there's no way I can graph the whole thing without lifting my pencil and switching from one section to the other. So we would say the 1 over x graph has a point of discontinuity or a non-permissible value when x is 0, because you're not allowed to draft that point. And when you try to graph it, you have to jump from one point to the other. Technically, we would say the limit as x gets close to 0 on this graph doesn't exist. Because as we get close to 0, there's no point it really gets close to. Down here it keeps going down forever. Up here it keeps going up forever. There's no real sense of where it's going to be as you get close to 0. But if a function is continuous, and you can substitute a point into that graph, you can solve the limit just by plugging in that value. And that's what we did with the 3x minus 8 question. So here, that's a parabola. Can you draw a whole parabola without lifting your pencil? Yes. So a parabola is a continuous function. How do we calculate this limit? We can just plug in 2. It's as easy as going 2 squared minus 1. The limit is equal to 3. What do you think? Could we teach these limits in grade 9? Probably. Here's another one. It's an x cubed graph. Is it continuous? Can you draw an x cubed graph without lifting your pencil? Yes. So that means I can just plug in -1 and solve and get my answer. So this isn't very exciting. Not too crazy mathematics. What we want to get into is what are the equations where we can't tell what's going on? How complicated can we make them? So we have to look at discontinuous functions. And we're going to call these first set of limits as 0 over 0 limits. In other words, when you try to plug in the number, you get 0 in your numerator and 0 in your denominator. And last, if you checked, if you go to your calculator and try to do 0 divided by 0, it is not very happy with you. Now, often in a 0 over 0 graph, you will often get a hole. And that's connected to some graphing that you did in grade 12. So here we can figure out this limit of this rational function. And the idea is going to be, just like in rational functions, how did you find the hole? You factored so that something would simplify. In this case, your x minus 3's would simplify away. And once that simplification has happened, well, then you look and say, well, now I just have x plus 3. Could I plug in 3 at this time? Yes. And so the limit as x gets close to 3 is 6. If we're looking, what does the graph of y equals x plus 3, x minus 3 over x minus 3 look like? Well, you have a non-permissible value, and I'm going to use NPV as an abbreviation. Again, mathematicians don't like to write too many words. A non-permissible value that x cannot equal 3. And because these factors simplify, that tells us that we will have a hole at 3 comma, and once they simplify, you could plug in 3 comma 6. So where the hole is related to the limit. Then if I wanted to graph this, after it's simplified, I just have this equation, which is y equals x plus 3. And that's a straight line. You're pretty good at graphing straight lines. Well, this straight line would have a y-intercept of 3. It has a hole at 3 comma 6. And this is what it would look like. And even though there's a non-permissible value at x equals 3, what the limit is saying is no matter which way you come towards x equals 3, either from the left side or the right side, no matter which way you come at 3 and get closer to it, your y values are going to get closer to 6. And so even though originally when you plug in the value and you get 0 divided by 0, in this case, it's equal to 6. So we just had a special case where 0 divided by 0 equals 6. Well, that's not actually true. We just figured out the limit, what it got close to at that point. So I guess I did this part of the slide already, where we figured it out graphically, right? We drew that line and figured out the limit. So in grade 12, we called that a hole. The reason we call it a hole because its other name was a point of discontinuity, which is way too many letters to write. Hole is a lot less. But those are both the same thing. So what we're wanting to do with these limits that can't be evaluated directly is we want to use all of our algebra skills, which we sort of was our preamble prior to this, factoring. If you can factor and something can cancel out, maybe you can evaluate it. So we're going to use our factoring skills. There's going to be ones with square roots that almost always use the conjugate, where you have to find out, use the idea of a difference of squares and figure it out. So that's what we're going to be looking at in our next couple of examples. So if you have a point of discontinuity, what we want to do is simplify the function by factoring or by multiplying by the conjugate so that that non-permissible value cancels out. And when a non-permissible value cancels out in a graph, that will result in a hole in the graph. If there's a hole in the graph, then the limit will be equal to the y value of that hole. That's the basic concept that we're looking at right now for a limit. So there's, on the next page, on page 8, there's 4 of them for you to try. Each of those 4, if you tried to plug in -2 right now, you would get 0 on the top, and you would get 0 on the bottom. Maybe we'll just do this first one together just for notation, okay? When you're evaluating a limit, you will always have to write the limit as x approaches -2, and then the algebra. So here is factoring a difference of cubes from what we did earlier. I can factor the a sum of cubes. I can factor the x cubed plus 8 as x plus 2 times x squared minus 2x plus 4. And I can factor the bottom as a trinomial to being x plus 2, x plus 4. Now, notation-wise, even though I'm just working with the algebra part, I need to rewrite the limit, and we need to continue to rewrite the limit until we evaluate it. So if in the next step I notice I can cancel out my x plus 2's and write the simplified form, I still have the word or the limit as x approaches -2 out in front. But now that I've canceled out that x plus 2, I can show it right here with a red line. I got rid of that non-permissible value. Can you see that now if you plug in negative 2 into your denominator, you're no longer dividing by 0. So we can now evaluate the limit by plugging in negative 2 for x. And as soon as you plug in the negative 2 for x, now you don't have to write the limit part anymore. So right now we're looking at what are the details for how to properly write a solution to something like this. We have to write the limit part until we're able to plug in the number to calculate it. And simplifying this, we get 6. Connecting it to what we've done in the past, we could say if we drew the whole graph, this would be a graph that has a hole at negative 2, 6. Because it was a non-permissible value, and then that non-permissible value went away. Every time a non-permissible value goes away, it still shows up on the graph as a hole. And the idea of a limit says, well, if you approach that non-permissible value, what's the y value going to be? Well, if you have a hole on your graph, it's pretty obvious that it's the y-coordinate of the hole. So your limit is really connected to something you've already seen in graphing from grade 12. Okay, so I'll let you try the next ones. Again, your goal is to play around with the algebra. You want to cancel out what's causing you to divide by 0. If you did, you would get an h squared on the bottom, right? Like you're saying multiply bottom by h and top by h?
Well, I need to get rid of it.
You need to get rid of that. So one way to get rid of it is if on the top you could factor out an h. Right? So if I had,
Because I factored.
yeah, you wrote that out. Oh, and it's squared, so they would both be minus, right?
Well, because it needs a negative.
Yeah, but h minus 3 all squared would be h minus 3 multiplied by itself, right? So you have this. Now what you want to do is you'd want to eventually, hopefully, dot, 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 be able to write the top as h times something so that your h on the top would cancel out with your h on the bottom. Okay? So maybe if you multiply this out and do some simplifying, maybe that'll work. Sometimes you don't know, but sometimes you have to try something. The other one won't be a hole. The other one will be a vertical asymptote. It'll only be a hole if it cancels out. So the fact that the x plus 2's cancel out, that makes it a hole. But if the other one doesn't cancel out, then it will be a vertical asymptote. I will put up the answer for the second one. Again, we want to do some algebra. So I multiplied this out, and my 9 and minus 9 nicely canceled, leaving with an h squared minus 6h in the numerator. Our goal, this is still 0 divided by 0. Our goal is to cancel out that h on the bottom. But now I can factor the top to be h times h minus 6, and my h's will cancel out, which just gives me the limit as h goes to 0 of h minus 6, which you can easily plug in to be equal to minus 6. So that graph would have had a hole at 0, negative 6. Okay? That's our goal right there, that step, to get those h's to cancel out. Because as soon as they cancel out, that's when you have a hole. Now, how you get to this step is your algebra skills. In this case, we had to multiply it out, simplify, and then factor. Yes, and you have to keep this limit as h goes to 0 all the way until you can plug in 0. So at this point, I'm like, oh, I can plug in 0 and figure this out. 0 minus 6, I guess. I didn't show you that. I hope you're okay. It's equal to minus 6. Then you don't need to write the limit part anymore. And we have a whole YouTube channel set up so that if you missed, yeah, but it's already working. Okay, awesome. And if you finish early and want to try some of the ones that are listed in the textbook there at the bottom, you can. And notice that I sometimes will indicate which are the ones that are really challenging. So if you're saying, oh, so far this isn't so bad, well, maybe you want to set yourself up and try those challenging ones. If the challenging one is too hard, maybe it means, hey, I do need some more practice with this and looking at my algebra skills. No, you won't be able to square root the whole thing with a plus sign in between. So this is one of the ones that you're going to have to use that rationalizing. Where, yeah, when we were rationalizing, by multiplying by the conjugate,
Like I multiplied this here and here?
here and here, by square root of x plus 16 plus 4 and square root of x plus 16 plus 4. And if you've got the next one and you're curious if you got it right, you can check with somebody else and say, hey, did you get 5? And then they'll say, no, I didn't get 5. Did you get minus 4? And they'll say, yeah, I think I got minus 4. This one, oh, it's now minus 4. If you see a square root, the strategy most likely will be rationalizing. How do you rationalize the denominator? You're going to need to multiply by the square root of x plus 16 plus 4 on both the top and the bottom. Right. Yes, and it's equal to that. But when graphing it, you're starting with this. Then this would be a hole. And your graph would just be x plus 3. This graph and this graph are similar, and they both look like x plus 3, but they have holes in different spots. This one would have a hole at 4. This one has a hole at 3. There could be, but we can't, if we have the original equation, you can't add a hole. You can only take the original equation and see if it has a hole. So this is true. You can multiply top and bottom by x minus 4, but it doesn't mean that the graphs are the same because you added something. And it's always based on what was there originally. So, like, this graph has a hole at 3, 6. Okay? This graph has a hole at 4, 7. This one has no hole. Y equals x plus 3 is just a line. They're the same formulas, yes. The graphs look similar, but if you start with this, it has a hole. You start with this, it has a hole. You start with this, it has no hole. It all depends what was asked originally. Yeah, you just have to be careful because if you do square root times square root, that square root will go away. And it'll just be x plus 16.
But then this, does that go into there kind of?
Yeah, and I would actually leave it, like here, I would leave it with a set of brackets like that.
Oh, the x goes to
Because you have to the x would have to get distributed if you wanted. So you'd have x times this plus 4x if you distribute it.
So I'll get rid of this pretty much, so just be x. And then,
Well, if you multiply the x times the square root would still be there. But what I'm saying on the...
it would be x squared, and then the square root of x over, wouldn't
Well,
it?
you wouldn't be able to put that square root easily in. You wouldn't be able to distribute the x inside because this has a square root sign. The only way we can multiply square roots, so for example, if I'm trying to multiply 2 times root 3, I can't do anything. But if I change the 2 to the square root of 4, then I'm allowed to multiply square roots. So our rules for multiplying square roots, which we did in grade 11, says you can multiply square roots if they're both square roots. This is okay. But I can't say this is root 6.
So how do I?
So I would just leave it like this. You're still going to have the limit here outside as x goes to 0 and the limit.
Can I put the 0 in already?
Not yet, right? Because we still have this x. If I put in the 0 here, it's 0 times all of this, it'd still be 0. But square root times square root, this will just be x plus 16 without the square root sign.
We can't get rid of those two 16s because
No, that's not, yeah, not a, but here, if I have x plus 16 minus 16,
it would just be x.
it would just be x. And then you would have exactly what you wanted.
And the limit is just like y.
The limit is the y coordinate of the whole. Now my x's would cancel out. Right?
So
Now I can, and now if I write it, I would just have 1 on top. And now you can ask yourself, if I plug in 0 now,
0 plus 16, that's
16, square root of 16 is 4. So then I would get 1 over 4 plus 4, 1 over 8. Yes? Square roots are always positive. You see the plus or minus? It's a good question. So the question was, is the square root of 16 4 or plus or minus 4? And the answer to it is square roots are always positive. One way that I can help you see that you've seen this before, do you remember graphing the square root of x? And it looks like this, right? It's always positive. It never has this bottom part. If you're solving an equation that looks like this, where you square root both sides, you add the plus or minus at that point. So that's a different kind of question. X squared equals 16 is not the same kind of question as x equals the square root of 16. X equals the square root of 16, the answer is only positive 4. X squared equals 16, the answer is positive or negative 4. And when you square root both sides is when you have to add the positive or the negative. Good question. Okay, let's check on this one. How did you do after rationalizing? Very nicely on the top, the 16s cancel. And we get to this stage which we wanted, where the value that was causing us a problem, the x, cancels out. That leaves us just with this, which you can plug in and get 1/8. For the last one, you got negative 18. You haven't got it yet. You got a fraction. Ooh, we got fractions, we got negative 18s. It's a good challenging one. And we got a fraction here, but a different fraction. And you got a fraction, and it's a different fraction. Should we do the last one together? Okay. Okay. Okay, so now everybody's whipping out their erasers and getting ready to go. Then it'd still be pi. Because technically, what does y equals pi look like? Is a horizontal line, that's always pi. Okay, so we see a square root on the bottom. The idea of conjugate comes into play. So I'm going to multiply the top and the bottom, and I'm going to change that sign, that's minus, to a plus. In my numerator, okay, with limits, we don't want to multiply things out that we don't need to. We will want to multiply out on the bottom, because that's what we were trying to do, a difference of squares. But in my numerator, I'm going to leave it. And in fact, I noticed that this can be factored to be x plus 4x minus 2. So I want to have it factored completely. Most likely, if you made a mistake, it was probably with positives and negative signs here. First of all, when you do multiply, and I'll put this in brackets, this difference of squares here, well, the square roots will cancel, and you'll just get x squared plus 5. It's a difference of squares, so there'll be a minus sign here. And then in the brackets here, I just expanded x plus 1 squared. So x plus 1 times x plus 1 would be x squared plus 2x plus 1. And it's important that that's in brackets, because this is, if you got a fraction or you got something wrong, it's most likely that you made a mistake, that you didn't subtract every part of it. Now, something nice is going to happen on the bottom. Can you see that this x squared minus this x squared is going to go away? And if we simplify the bottom, we're going to be left with a minus 2x and 5 minus 1 plus 4. At this moment, when you look at the limit, can you still see that you have a 0 on the bottom if you plug in 2? But our goal is to cancel out that non-permissible value. So we can factor a negative 2 there we go. Factor a negative 2 out of the bottom. And all of that algebra was just so we could get to this wonderful point where we say those cancel out. Because that was the value that was causing us problems. And if it cancels out on the top and the bottom, On a graph, that means you just created a hole at that point. Now what's left? Even though it's still not the nicest looking, now we can plug in the value of 2. And evaluated, comes out to be minus 18. So take out your textbooks. Try those examples on page 19 and 20. Again, you probably don't have to do them all, but there are some that are a little bit complicated. If you don't have your textbook, you can pull it up on Teams, the PDF on Teams. You may. And I got to change my clock at the back because it is off by 5 minutes, which is causing me all sorts of problems. Kate, what time does it say officially on your phone? 3:01. 3:01. Mm-hmm.
Would you also, what is the word, rationalize?
Yes.
Cube root the same way you would if you
Yes. Well, no, not the same way. For this one, I would rewrite the x as the cube root of x cubed. Does that make sense that that's the same as x? And then I have something cubed minus something cubed. Tricky, eh? And so you'd have to factor the top. It doesn't look, it just looks like x minus 8, but you actually have to factor it as a difference of cubes. Do that right now. And I'll officially stop our video.